This is a lecture about nomenclature, naming for both ionic and covalently bonded compounds. Just a quick review here to make sure that you are reading chemical formulas correctly. Subscripts in a chemical formula tell us how many of each type of atom are present. So, of course, in H2O, that's telling us there are 2 hydrogen atoms and 1 oxygen atom. There are several different ways that we represent chemical compounds, different types of formulas. Probably the most common is just simply a molecular formula, which is a summary of the different types of atoms and how many of each, but it doesn't tell us anything about the structure of the compound. So what's more informative is a structural formula. So you see here, this is still C6H6, but it tells us something about how the different elements are connected to each other. These space filling models, you can actually purchase molecular models, somewhat similar to the ball and stick models, but the thing I wanted to mention in all of these is there is a color code that chemists use that's universal, and that is that black balls always represent carbon, the element carbon. White represents hydrogen, and red represents oxygen. Those are probably the more common ones that you're going to run into, especially if you take organic chemistry. All right, so let's go ahead and start learning the rules for naming covalent and ionically bonded compounds. Again, a quick reminder, a covalently bonded compound arises when 2 nonmetals combine to form a bond, and we call a covalently bonded compound a molecule. Now, that may sound almost too obvious to mention, but the reason I bring it up is because an ionically bonded compound, which is formed when a metal and nonmetal combine to make a bond, is not called a molecule, okay? We refer to a unit of an ionically bonded compound, so for example, sodium chloride, as a formula unit. So when you come across formula unit, I want you to kind of think molecule, okay? We'll talk about where that name came from later on. All right, we're going to start with the easy ones, which is covalently bonded compounds or molecular compounds. And so the first word of actually any compound, whether it be molecular or ionic, is simply the name of the element. So if we have something like CO2, okay, you would start that name with carbon, simply the name of the first element in the formula. For the second part of that word, that's usually what gets just a bit more involved. You start with the name of the element, but then you give the element the suffix IDE, okay? So this is oxygen, so what that rule is telling us that you start with oxygen, but then change the ending to IDE. So in this case, it would be oxide, right? Now, probably the most important thing and difference to remember when naming covalent compounds is that you must use prefixes to tell the reader how many of each type of element is in that compound. So again, looking at CO2, it would be carbon dioxide. Okay, and I think we all know that di stands for 2. That's telling the reader there are 2 oxygen atoms in carbon dioxide. So it's important to memorize the prefixes 1 through 10 here. Now, you may or may not have noticed that I did not write a prefix for the carbon. And that is because when there is only one of the first element, you do not have any prefix. It's understood, it's implicitly understood, if there's no prefix before the first element, that there's only one of them. So that's what you see in parentheses here. Now, when we get more into writing formulas, so in other words, you need to go in both directions. You need to be, if I give you a formula, you need to tell me the name. If I give you the name, you need to be able to write the formula. So if you're writing formulas, the rule is the element that has a smaller group number, in other words, the element that is farther to the left on the periodic table, is always shown first. In some textbooks, you'll see that described as the element with the lower electronegativity shows first. Same thing. So let's look at some examples. Pretty easy, I think. So here are some examples where we're giving a formula and asked to write the name. Nitrogen, so remember, don't put mononitrogen. Dioxide, and then dinitrogen. Now this is probably the most commonly missed prefix for 4 of an atom. Tetroxide, and dinitrogen, because there's 2, and then pent stands for 5, pentoxide. So you need to be able to go in the other direction too. You need to be able to be given the name and write the formula for that. All right? So covalent names, pretty easy. This is kind of trivial, but I want to point it out anyway. Whenever you start writing a prefix, so penta is the prefix for 5, and let's say oxide. When there are 2 vowels that would be put together, the first vowel is dropped. So instead of writing instead of writing pentaoxide, it's pentoxide. Okay, and that first vowel is crossed out. I should probably change colors, shouldn't I? There we go. Naming ionic compounds gets a bit more complicated because there are so many different types of ionic compounds. So we're going to start with the easiest, and that's binary ionic compounds. Binary simply means there are 2 different elements in that compound. All right, so we'll start with those first. The cation is always named first, and you'll notice the cation in formulas is always shown first. That's a pretty important rule. See, you will never see sodium chloride written with the chloride first. Okay, so always the cation, always the metal first, okay? And just as in naming covalent compounds, the first part of the name for an ionic compound is simply the name of the element. Okay, so NaCl, the first part of the name is sodium. No prefix, no suffix. And then, of course, that leaves the anion. The anion is named second, and it is given an IDE ending, just as when naming covalent compounds. So that is chlorine, so we're going to call it chloride. So far it's reasonably similar to covalent naming. What are the differences? Never, ever, ever use prefixes when naming ionic compounds. And you don't need to, because whereas covalently bonded compounds can combine in a number of different ways, for example, if you are looking at the elements carbon and oxygen, they can combine to give carbon monoxide or carbon dioxide. Because of the different ways and the different ratios the elements can combine in making a covalent compound, we have got to tell the reader what ratio they were combined in, and that's what the prefixes is for. Now, in an ionically bonded compound, they can combine in only one ratio because they're charged, right? So every single compound as it exists in nature is overall neutral. Okay, so even though ionic compounds have cations and anions, overall their net charge is 0. And because of that, if we have a cation and an anion that form a bond, they can only combine in one ratio that will make the overall charge 0. And because of that, we don't have to tell the reader, we don't have to use prefixes, because the reader can figure out based on the charges what ratio those elements combined in. So let's look at some examples of that. Alrighty. So let's do naming first. That's a little bit easier than writing formulas, I think. All right, so always the cation will always be shown first in the formula. So just the name of the element, that's magnesium. And then the anion, the second part of the formula, you start out with the name of the element, oxygen, but then you give it the suffix IDE, just like we did with covalently bonded compounds. And now we have sodium oxide, no prefixes, right? So you got to remember that. And aluminum sulfide. Pretty easy. Now, this is where I really want you to tune in. This is really, really important what I'm getting ready to say. When you write formulas for an ionic compound from its name, it is a two-step process. Very, very important not to shortcut that, okay? The first step is write the charge of the anion and cation. Okay, so calcium phosphide. Don't just write the symbol of the elements, write the charge. These are ionic compounds, they have a charge. You have got to memorize the common ion charges for each group number. So calcium's in group 2A, which means that calcium ion has a charge of 2+. I have no idea where phosphide came from. Okay, we'll say oxide. There we go. All right, oxygen is in group 6A, which has common ion charge of -2. All right, that's step one. Step two is then combine the charges, so the net charge over, combine the ions, so that the net charge is 0. Okay, so in other words, you want the total positive charge to equal the total negative charge. And if the charges are the same but opposite here, you just put them together in a 1-to-1 ratio. All right, so let's look at another one for a moment. Move that up. All right, lithium nitride. Step one, write out the ions with their charges. Okay, so lithium and nitride don't have the same but opposite charges. And we are going to need 3 lithium, since it only has a +1 charge, in order to balance out 1 nitrogen with a -3 charge. So if you need to literally write them out, then do that. Okay, whereas you would add all of the exponent charges together and make sure they add up to be 0. Now, probably the trickiest ones as far as determining ratio are when you have an odd and an even number mixed. So let's look at aluminum oxide. Aluminum has a +3 charge, oxygen has a -2 charge. And so to get that to balance out, you would need 2 aluminum. So I'm going to go ahead and just write that out for you. And you would need 3 oxygen. So let me show you why that is. All right, so you have +6 on the cation side and -6 on the anion side. Okay, so the formula for that would be Al2, because you have 2 aluminum, and O3. Now, a little trick way to do that, which you may have learned in high school, is we call it either swap and drop or crisscross. So when you do step 1 and you write the charge of each ion, then crisscross. So we take the charge of each of the ions and it becomes a subscript for the other ion. So the 3 charge in aluminum goes down and becomes a subscript for the oxygen. Don't carry the plus and minus down. That would be nonsensical. And the 2 charge on the oxygen would come down and become a subscript for the aluminum. All right? Now, one thing you need to be careful of if you're going to do this swap and drop thing is that if you swap and drop and the ratios of ions you get can be mathematically simplified, you must do this. Now, I'm going to emphasize this is only for ionic compounds. Don't get confused and start simplifying covalents. All right, so let me show you. So here's a really good example. Calcium and oxygen. If you did swap and drop without thinking, like hopefully you'd see, okay, the charges are the same. I'm just going to put them together in a 1-to-1 ratio. But if, let's say you had test anxiety and you just swapped and dropped, you would get this, okay? That is not the same thing as calcium oxide, and you would get it wrong. So what you have to remember is if you're going to swap and drop, look at the subscripts, and if they can be mathematically simplified, in other words, both of these can be divided by 2 to be simplified, you must do so. This page just kind of formally lists what I said about swap and drop or crisscross. And I kind of like the lead oxide example here because that's something I can see most of you using the swap and drop method for. And this would be a perfect example where if you didn't simplify mathematically the subscripts, you would get it wrong. Notice that both of these subscripts can be divided by 2. So it can be simplified to PbO2. All right? So just make sure you remember to do that. If you have an ionically bonded compound that contains a transition metal, so that is one of the D block metals, the naming and writing formulas gets a bit more complicated, and that's because most transition metals can have multiple charges. So you don't ever have to memorize these. I'm just kind of making the point that you don't necessarily know what the charge is going to be when a transition metal forms an ionic bond. Whereas for the A group, for the most part, we can predict that the charges will always be one single thing. They won't vary. So because of that, naming gets a little bit more complicated when we have transition metals. And there are a couple of metals outside of the transition metals that also have variable charges. The ones that you will see more often and the one that you should commit to memory are tin, Sn, and lead. So just remember you have to treat them as a transition metal when you're naming. All right, so let me give you an idea of what might happen. So iron, turns out, can have a charge of +2 or +3, depending on the conditions, depending on the other element it encounters. So you have to figure out what charge it has. So let's say we're given a formula like this. What you always want to do is start with the anion, okay, to determine the charge of the cation. Start with the anion charge because the anion charge is typically known. Remember, it's just the transition metal that has variable charge. So what is the common charge on a sulfur in an ionic compound? It's in the oxygen group, so it's -2. And now remember that an overall compound has to have no net charge. So that means iron in this case has to be +2. And here's an example, iron with a +3 charge. Okay, we know that nitrogen group has a -3 charge when it's an ion, which means in this case, iron has to have a +3 charge. So how do we tell the reader what the charge of that is? So if we have something like FeS, we have got to tell the reader that we are not talking about, that we're talking about an iron with a +2 charge. And we do that by using Roman numerals in parentheses. Okay, so the Roman numeral represents the charge on the transition metal. Okay, charge on a transition metal. So if we were naming this, we would call it iron, parentheses 2, sulfide. Right? And if we were naming FeN, it would be iron 3 sulfide. Yeah, so make sure if you're rusty on your Roman numerals, make sure you know how to write them all. So every time you see a formula, you should ask yourself a series of questions. One, is it ionic or covalent? That should be the first question because that's going to make a big difference. So in this case, I know this is ionic because I know that chromium is a metal. So the second question should be, if it's ionic, is there a transition metal? Because that's going to determine whether or not you have to use Roman numerals. All right, in this case there are. So if there's a transition metal, then you have to determine the charge on the transition metal. And so again, determine charge of transition metal by starting with a charge on the anion. Okay, I'll just say by looking at anion. All right, so we know that bromine, being a halogen, as an ion has a charge of -1. There are 3 bromides in this compound, so the bromine overall contributes an overall negative charge of -3. 3 times -1, right? For this whole compound to be neutral overall, that would mean chromium, in this case, has a charge of +3. So what would we call this overall? The first part would be chromium, parentheses, Roman numeral 3, and then the ending would be bromide. So let me pull that up here. There. Okay, chromium 3, bromide. See if you can do this on your own. I would recommend turning off the video, giving it a shot on your own, and I will just give you a hint here. Even though tin is not a transition metal, it is one of the 2 I said that behaves like a transition metal, so you have to use Roman numerals with it. Alrighty. Now, keep in mind that when you're given a quiz or a test, the naming is not going to be separated into a list of ionics to name and a list of covalents. They're going to be jumbled up. So make sure you ask yourself, is this ionic or covalent? It is ionic because iron's a metal. And to make my life more difficult, it is a transition metal. So I know that I am going to need parentheses with a Roman numeral. So I automatically get in the habit of writing parentheses as soon as I see I'm dealing with a transition metal. I also happen to know that's iron, so it's pretty easy to write. Okay. Now, I know the ending name is going to be nitride, that's nitrogen. So it doesn't matter what order you determine these parts, that's how I approach it. Then the last thing I do is figure out the charge on the ion. Again, you need to start with the anion. So I'm going to draw this. I've just noticed that sometimes this helps students. I'm going to draw a box for each atom. Okay, so I have 2 nitrogen atoms. There's a subscript 2. And I have 3 iron atoms. Okay. Again, you don't necessarily have to draw this out. It just helps me visualize it. I know the charge on each of the nitrogen atoms. Nitrogen, when it's an ion, has a charge of -3. So my total negative charge is -6. I know now that my total positive charge must be +6 in order to balance out the negative charge. So if my total iron charge has to be +6, what is the charge each iron atom must have? +2. So the name of that would be iron, Roman numeral 2, because you're writing the charge on one individual transition metal. All right, now to go the other way, tin oxide, a little bit harder, but remember when you're going from name to formula, remember it's a two-step process, okay? The first step is to write the symbols with their charges. So there we have tin. They gave you the charge. Just remember that's what the Roman numeral represents, is the charge of the metal. And then oxide is the second part. And I know the oxygen has a -2 charge. All right, if you swap and drop, I'll just do that here. Get this. Now, again, do not forget that if you can simplify, you must simplify. And I can here, okay? That simplifies to SNO2 because both of these subscripts can be divided by 2. And so this is the correct formula for tin 4 oxide. That takes quite a bit of practice, so I strongly recommend that you print out as many practice worksheets as you can on naming and writing formulas. All right, we're closing in on the end of naming. It turns out that some ionic compounds, and it's usually the anion, have a polyatomic ion in them. So what is a polyatomic ion? I'm going to show you first what is not a polyatomic ion. So a monoatomic ion is only one type of ion. So oxygen, the monoatomic, there's only one type of element in the ion. Nitrogen, okay? So those are all monoatomic ions, okay? One type of element. A polyatomic ion has at least 2 different elements in it, okay? So let's look at a common polyatomic ion called acetate. It has carbon, hydrogen, and oxygen in it, all right? And so this table lists the more common polyatomic ions and ones that you should begin memorizing. Now, when you memorize these, it's important not to just memorize the name and the formula. Make sure you also memorize the charge. Let's look at some examples of naming ionic compounds that contain polyatomic ions. First thing that you have to be able to do is recognize that you're dealing with a polyatomic ion, okay? So the approach I take, for example, if I were to look at that formula, I'd say, okay, it's ionic because I see a metal ion first. And then look at the anion part. It's typically the anion, like I said. There are a couple of cationic polyatomic ions, but most are anions. And then I would say, oh, the anion has 2 different elements in it, therefore is a polyatomic. So it's a pain to memorize all those polyatomics, but once you memorize them, it's a little bit easier to name than some other ionics. So the name of this, as always, you start with the cation, just give it the element name, sodium, and then it's simply memorizing. So NO2 is called nitrite. Okay, NO2 is called nitrite. So the name of this ionic compound is sodium nitrite. Now you got to be really careful because there are a lot of similar polyatomics. So whereas NO2 is nitrite, NO3 is nitrate. So be real careful with that. Here's one for you to try. If you need to skip back to, you may want to print out the list of polyatomic ions or make some note cards or something. But turn the video off, give this a shot, see how you do in naming these, and then turn it back on. I'll work it out for you. All right, so for this first one, I want to point out, be really careful because students get magnesium and manganese incorrect. Mn is manganese, all right, and it is a transition metal. So, but I know manganese, I'm going to put parentheses to remind myself that it's a transition metal and needs a Roman numeral. I'm going to recognize that this is a polyatomic NO2, and I'm going to look on my list because I probably haven't had them memorized yet. I'm going to see, okay, that is nitrite. So I know that it's going to be manganese something, some Roman numeral nitrite. So now I have to figure out the charge on the manganese in this compound. So I'm going to do my little pictures. I have 2 nitrites. I'm going to draw my little boxes for them. And each one of those has a -1 charge. So my total negative charge is -2. So that tells me that the manganese has to be +2. There's only one manganese in this. All right, so my final name then is manganese 2 nitrite. So let's go in the other direction now. Number 2, let's look at a name and write a formula. And again, I'm going to sound like a broken record. Anytime you're given a name and you're told to write the formula, it is a 2-step process. So copper 2, I'm going to write the cation with its charge. Now, phosphate, how do you know from a name that it is a polyatomic ion? So always on a test, and I know it's test anxiety, I'll have a student raise their hand and say, well, when we taught face-to-face anyway, I can't find phosphate anyplace in the periodic table. It's not an element. How do we know that? Just by looking at the name. Okay. If it ends in ate or ite, it is a polyatomic ion. Okay. What is the ending? What is the suffix when it's just an ion from the periodic table? Okay. If it's from the periodic table and it's an element, it'll end in IDE. Now, heads up, there are a couple of polyatomics that also end in ID, and that's why it's so important to start memorizing them, okay? All right, so phosphate ends in ATE. It's definitely a polyatomic, so at this point you probably have to look it up, right? Turns out phosphate is PO4, and it has a 3- charge. So let's go ahead and find the formula by crisscrossing charges. All right, that's going to come down here. Now, when you're dealing with polyatomic ions, it's helpful to enclose the polyatomic in parentheses because you're going to end up with 2 subscripts next to each other. So here's copper, and I'm going to have 3 copper, right, because this 3 from the phosphate came down. I'm going to put parentheses. I'm going to enclose my polyatomic ion in parentheses, and then I'm going to carry down the 2 as a subscript. Now, see, if you didn't put the parentheses there, it would look crazy. It would look, see, 42 or something. Okay, so be real careful when you're dealing with polyatomics to put them in parentheses. Now, I didn't used to teach naming for hydrates, but then I saw it on a couple standardized final exams, so I thought just real quickly mention it. There are some ionic compounds. Well, most ionic compounds will dissolve in water, which means they have an affinity for water. And so some ionic compounds have a strong enough affinity for water that they will actually suck out the water even from the air, and they'll incorporate the water molecules into their crystalline structure. And so the water molecules are actually become part of the beautiful structure. So they're literally part of the compound, not just hanging out. And so in that case, when that happens, we call those hydrates. So you can see here we have magnesium sulfate. And if there's a little dot there, that means it's a hydrate. That means that the water molecules are actually complexed and arranged in a regular pattern with the ionic compound. So how do you name those? Well, the ionic part is named as normal, so that would be called magnesium sulfate. And then you just add a third part onto the name that tells you how many water molecules are complexed with one ionic formula unit. And so you have to, again, you have to know your prefixes. 7 means hepta, so it's just simply magnesium sulfate, heptahydrate. Here's another one, okay? Name the regular part of the ionic compound normal, tin. Tin behaves like a transition metal, so you need to find its charge in a Roman numeral. Chlorate is the name of the polyatomic ClO3. Tin to chlorate complexes with 5 water molecules, so then you just add pentahydrate. So that just may help you on a random final exam question. That's it for naming.